Okay, good afternoon, everyone. Welcome to the first afternoon session. The first speaker is Professor Myung Kim from Korea University, who's going to be talking about infrared surface plasmons in 2D material.
Thank you for the introduction. Okay, so good afternoon, everyone. My name is Myung Kim. I'm from Korea University. So it's my great pleasure to be here, and I really appreciate to Professor Yong Cho and all the organizers. Okay, so today I prepared this topic, the exploring shortwave infrared surface plasmons in 2D MXene structures. So this is the new. Okay, so this is a new material. It's artificially synthesized material, not naturally occurring material. So MXene can also be used as the photonic devices or optical materials. So today I want to show that topics. So this one was co-worked with the Professor Yuri Koguchi at Drexel University and Jongmin Koo at Sungkyunkwan University and me, my team. Okay. Okay, so as many of you know that the 2D material is the very exceptional material. This is very anisotropy material, as you know that. So two-dimensionally, the atomic structure is this symmetry, but the vertical direction, this structure is very the single atomic structure or several few layers of the atomic structures. So 2D materials is discovered from this single element structures like the graphene and black phosphorus and so on. And sometimes we can get the non-metallic compound like the hexagonal boron nitride and the structure. Recently, people are interested in the metallic compounds based 2D materials, such as the TMDC materials. So sometimes the organic materials can generate the 2D material structure, and sometimes the salt also can generate the 2D materials. Due to this very exceptional the structural property of these 2D materials, they shows the very exceptional properties, such as for example, if you see the graphene, the mechanical and electrically, this is very high properties. So mechanically, it's very strong mechanical it combines, and electrically, it is very high conductivity. Even the structure, even these properties, this structure shows the very transparent, and the thermal conductivity is very large and impermeable and lubricable. Yeah, so this is very exceptional properties. So due to this, the outstanding properties, the 2D material, for example, graphene shows the very many applications, such as the energy applications, environmental sensors, and even the biomedical applications. In 2012, the graphene-based plasmons has been discovered. It's published in Nature. It shows that the field, the plasmon properties is generated at the interface between the graphene and the dielectric materials. So graphene shows the very strong field confinement, and it generated the plasmonic properties in the graphene structures, so 2D material structures. This field confinement is very larger than the conventional metal based the plasmonic properties. So as you can see here, so if we compare between the noble metal structure and the graphene structures, then we can clearly compare that the field confinement is extremely enhanced by using these 2D materials. There's the very thin structure, and the opposite, the charges are generated in this very thin structure. So it generated a very extremely large field confinement with this 2D material-based plasmonics. But there is one issue. That is as you can see here, this shows the dispersion relation of plasmonic surface plasmon polaritons of the noble metal structure and the graphene structures. So as you can see here, the noble metal the plasma frequency is going to the visible region if we use the noble metal structure. But if we use the 2D material, for example, the graphene, it cannot go up to the SWIR, near IR, and visible regions due to the very low electron density. So we simply can think that this structure is very thin, as it's very hard to get the high electron density. So, okay, so we want to use this 2D material as a photonic devices, but there is some limitations to get the large electron density or large plasma frequency or large surface plasma frequencies. So there is the limitation of the 2D material-based plasmonics. So you can see here the graphene in the dispersion relation. Graphene is located this way. Okay, and the noble metal copper, gold, silver, aluminum is going to the visible regions. So even if we added a high doped region, high doped property to the graphene, it's still difficult to get the large electron density. So we can compare this one. So heavily doped graphene has this value of the electron carrier density. Black phosphorus has shown this one, but the even 3 nanometer thick gold structure is very large electron density. So this discrepancy makes the graphene plasma frequency makes it difficult to go up to the high frequency region. So SWIR, near IR, and visible region.
Excuse me. Last question. Do you have surface plasma, two-dimensional plasma?
Yes, right. So what's your question?
Is it surface plasmons or two-dimensional plasmons?
2D material plasmons. I currently say about the surface plasmons in the 2D materials. Yeah, at the interface between.
Because as far as I know, these two objects are quite different. So for surface plasmons, there's some strong graphene, and two-dimensional plasmons, which are sort of three-dimensional but transferred to two-dimensional case. So how do you distinguish the nature of this plasma?
Okay, so thank you very good question. So surface plasmons is generated at the interface between a dielectric and metallic structure. These two actual values should have a different positive and negative values, opposite values. So based on this condition, based on condition, the surface plasmons can be generated at the interface, right?
So it's very important to have some bulk also connected to the dimensional interface.
Yeah, right. Yeah, but in that case, the graphene or metal structure should have the conductive material, the metallic structures. Yeah.
Okay.
Yeah.
I want to figure out what I don't think you necessarily need graphene to be sitting on a 3D surface. You have suspended graphene, for example, right? Just suspended, and you have these ribbon-like structures drawn in it which can confine, like a resonator, say lambda over 4, or lambda p over 4, words of the you'll still see plasma resonance.
Yeah.
So freestanding graphene can support plasma on this confined into resonator structure, or if you shine light at a not normal incidence scale.
But still, the role of the media is played by the great structure.
Would get pure if you shine light then at a different wavelength. If it is unpatterned, say just freestanding graphene, you get it.
Yeah. Thank you. Very good point. Yeah. So anyway, so important thing is that the graphene or 2D material should have the metallic properties to get the surface plasma at the interface. Okay, so but typically, many of you know that the 2D material is the semi-metal, right? So it's not completely metal structure. Okay, so yeah, so we want to use these properties using the 2D materials, right? So today, I want to introduce the new 2D material of the MXene. Okay, so MXene. Okay, so I want to briefly introduce how to make the MXene and how to operate this MXene structure. Okay, so let me see here. Okay, so MXene. MXene is synthesized from a max compound. Okay, so max compound. So max compound means that the N is the early transition metal M, and the A is the A group, including the aluminum and this group. Okay, so early transition metal here, and the A is the A group material, and the X is the carbon or the nitrogen materials. Okay, so max compound. So we get from we make this mass compound the first step, and then by etching this A layer, okay, by etching the A layer, this compound changes to the 2D material structures by adding the surface group functions to this structure. So MXene is generated from the MAX compound, and we added an ANE suffix to emphasize its electric conductivity. Okay, so MXene is the MXene. Okay, so MXene is like that. Okay, so currently more than 30 different types of MXene have been synthesized. So we simply think that there are many options, right? There are many options to generate the MXene structures. Okay, so the MXene is a two-dimensional nanomaterial with a thickness about the 1 nanometer. So it is completely 2D structure, but artificially synthesized 2D materials, not naturally occurred 2D materials. So we can get many options artificially to make a MXene structure. So MXene possesses a high density of hydrophilic surface functions group. So hydrophilic surface functions, hydrophilic surface functions, that means it is separated automatically, separated to make the 2D structures. And this structure has the very high conductivity. Okay, so very large electron density because it is generated from the early transition metal compound. Okay, so this is artificial material. Okay, so simply we can see that there is the max page, right? Max page, and then by using an HF solution or any other solutions, we can selectively etch the A layers. Okay, so it generates the MX, right? But the surface group function is attached at the surface of MX layer like that. So there is the surface group function. So MXene is generated as the 2D materials using this process. Okay, so this is a web process and very the large scale process. So we can make the very large compound, many large. We very simply make these 2D MXene structures. So this is the next phase is here, and by etching using the HF solution, it generated like MXene compound, MXene solutions, and then by using a spin coating, we can get the MXene 2D layer structure. So TM structure shown here, and if you see the diffraction patterns, the crystal lines is clearly shown these 2D MXene structures. Okay, so if you see the TM image, we can see like the MXene structure like this, the layers, the atomic layers, and with the L spaces. So surface functional group cannot detach, attach each layers. So this is like 2D material. So sometimes we can make the the single layer MXene structures. Okay, so there are so many types of the 2D MXenes by choosing how's the MX. So by choosing by the combination of how to choose the compounded element, we can make the various types of MXene structures. Okay, so there are so many options to get the 2D MXene structures. Okay, so. Yeah, so there are so many superior characteristics of the 2D MXenes. For example, the high electrical conductivity. Okay, so and this MXene shows the solution processability and optical transparency, surface reactivity, and the tunable work function is possible by combination of each MX element. So it shows the very high performance in various applications like the electromagnetic shielding, energy storage, sensor, and the flexible electronic devices, electrons. Okay, so in this talk, I want to show the MXene can be used as the plasmonic device, plasmonic materials or photonic materials by using the high electron density in this 2D MXene structure. Okay, so yeah, anyway, so we show the large electric magnetic shielding effectiveness of this MXene structure due to the very large electron density or large the conductivity of this MXene. Okay, so So here, if we measure the permittivity of this 2D MXene structure, we clearly see that the plasma frequency, okay, which means the epsilon equals 0, real epsilon equals 0, is located in the SWIR or NIR region. Okay, so that means that the MXene shows the very high electron density. Okay, so this is very interesting property compared to other 2D materials. So if you compare the electron density, this is the 2D electron density, 2D density of a carrier. We can see that the MXene has the very large electron density compared to other 2D materials, and it is comparable to the conventional, the noble metal structure. Okay, so very thin structure, 2D material, but MXene shows the very large conductivity or electron density. So we can use this MXene structure as the 2D material-based plasmonic devices. Okay, so yeah, so this is a very key property of this MXene plasmons. So based on this electron density, we can estimate that the MXene dispersion relation is located between the gold and the copper regions. Here is the SWI, shortwave infrared regions, 1 micrometer to 2 micrometer regions. So very large, high frequency regions. MXene plasmons can be generated in their region. So we can use this device as the communication devices, any other IR-based applications. Okay, so the other interesting property, optical property of MXene, in this case, we use the titanium carbon Ti3C2TX. Okay, TX is the surface group, and the Ti is early transition, and carbon we used. Okay, so the other optical property of MXene is the very high nonlinear coefficient. Okay, very high nonlinear properties. We can simply think that this is the 2D structure, like 2D structure, and the air gap is generated between these two layers. If you shine the electromagnetic field to this structure, it is oscillated, right? It's oscillated, but there is a very many the surface terminations. So it's a very high chance to get the large nonlinear coefficient to this structure. Okay, so and the Ti3C2TX has the very low electron band gap. So this property makes the very large optical nonlinear coefficient of this structure. Okay, so we explored the giant nonlinearity of this MXene structure in the shortwave infrared regions, okay, SWIR region. So we explored the MXene can generate the large nonlinear responses from this structure. Okay. Okay, so this shows the TEM imaging, and the MXene structure is layered on top of the quartz substrate, and we can deposit the SiO2 layer and so on. And we measured using this structure. In this case, the thickness is about the 5 nanometer or 5 to 7 nanometers. But regardless of the layer numbers, we could get the very similar permittivity of this the MXene Ti3C2TX MXene structure, and clearly we see that so plasma frequency is located in the IR region, okay, SWIR region. So it still shows the very large electron density. But the issue is that if we use the single interface between the MXene and the dielectric layer, the field confinement is very low because the absorption coefficient is large imaginary permittivity values of this MXene structure. So if you compare the dispersion, the air dispersion and air max dispersion, the effective index is very low. Okay? It's very similar to the air, so it's very hard to use this simple structure. However, if we use the very thin metal MXene structure, okay, so for example, if you reduce the MXene thickness less than 10 nanometer, we can get the large confinement of the plasmon, surface plasmons in this structure. So 2D materialists, they still have the always have the good property of a surface plasmon confinement due to the opposite charges generated between these two surfaces. So as you're reducing the MXene structure, okay, the thickness of the MXene structure. So if we use like a 2D material structure of MXene, we can get a very large surface plasmon confinement in that structure. So we clearly see the wavelength is critically reduced as reducing the thickness of the MXene.
Excuse me. Are we talking about a monolayer still, or it's more like this structure?
No. In this case, we just use the 5 nanometer in the experiment.
5 nanometer.
Yeah.
It's a monolayer.
Yeah. It's very currently we just use the 5 nanometer structures. Yeah.
And this density that is about 15 it's for.
Yeah. So
it also depends on this. Right.
Yeah, but the 2D density is quite similar. Okay, 2D electron density is quite similar, but the vertically, if we find the 3D density of the electron density, it still shows very similar values. Yeah. So in the experiment, we use the 5 nanometers. The smallest thickness is 5 nanometers, and it is a simulation. Okay? So 10 nanometer is very critical to get the smaller wavelengths, the large K vectors. Okay, so anyway, so field is tightly confined near the MXene structures by generating the surface plasmon polarities. Okay, so this is a graphene structure, but even the graphene structure, to increase the field confinement, they used the acoustic plasmon model. So that means by going to the MXene structure with the gold layer, field is more tightly confined in the graphene structure, graphene plasmon structure. So if we introduce this acoustic plasmon model to the MXene, we can also get this very high field confinement of these plasmons. So we also compare that if we introduce the gold layer on top of the MXene layer, we clearly see that the acoustic MXene plasmon model is generated in this structure. And so here the 5 nanometer means the MXene thickness, okay, and the AMP 10 nanometers max thickness, and the MP means the without the acoustic model, just the pure the MXene structure. So first we can compare the green and blue line, and it shows the increase the wave vector numbers. And then if we reduce the MXene thickness, we can further increase the wave number of this plasmon mode. Okay, so and if we reduce this space size, then we further get the large effective refractive index of surface plasmons. So SWL region, okay, so IR region, MXene can generate surface plasmons, and the field confinement can further be increased by introducing the acoustic model structure and reduce the spacer and the thickness of the MXene. Okay, so there is the direction to get the useful the MXene plasmons. Okay, so it's just the MXene and SL layer and the gold structure, and then we measured the TX, the permittivity, and it shows very similar value, even with the different thickness of MXene. And we can clearly compare that the pure MXene structure is the very poor the confinement, but by introducing the acoustic plasmon model, the MXene plasmon confinement is very tightly confined within the SI of the spacer layer. Okay, so based on this, the AMP model, okay, acoustic MXene plasmon model, we designed the resonator structure to increase the coupling between the incident beam and the MXene plasmon structures. So we use the larger structure. So first, we experimentally verify that the MXene plasmon model exists in real experiment. So we change the size of the large structure, and we choose the spectrums variations as a function of geometric change. Okay, so we changed the length of the large structure, and this is simulation result, and this is experiment result. So clearly, we see that these two trends are very similar. That means the MXene plasmon model is generated in that structure. Okay, so resonance P is generated from the plasmonic model. Okay. So clearly, we see that the MXene, acoustic MXene plasmon model exist in the form of the plasmons in the structure of the AMP structure. Okay, so we found that the MXene plasmon model exists in this M model structure, and we know that the MXene has very large optical nonlinear property. Okay, so the large field enhancement and the large nonlinear properties, we can expect that this MXene-based plasmon structure provide the very giant nonlinear properties compared to other 2D materials in the SWIR regions. First, we measured the persistent MXenes the N2 value, okay, the nonlinear values. So this interests me. This nonlinear value is also has a function of the MXene sequence. So as you reduce the MXene sequence, we can get the large nonlinear coefficient of this MXene, pure persistent MXene structure. Okay, so this is the real N2 value and immediate N2 value. The real N2 value means that we can expect the very large third harmonic generation from this MXene structure, and immediately and largely immediate N2 value gives the chance to increase the extremely large absorption, nonlinear absorption in that structure. The field enhancement or intensity enhancement can also be as a function of the MXene sequence, as I mentioned. So as you reduce the MXene sequence, we can get the very large field enhancement. So using these two parameters, okay, using these two properties, we can expect to get the very large nonlinear responses from this MXene structure. Okay, if you use the MXene structure of 5 nanometers. Okay, so we tune the structure to increase the field enhancement. Okay, so the rectangular, the asymmetric structure is used for the gold layer here, and the MXene layer is located here, and the SF2 tracer is here. So this is fabricated structure. And we first measure the transmission spectrum using this structure, and we clearly see that the Y polarization, the spectrum is measured, shows the resonant frequency of the SWIR. So communication wavelengths, even with the 2D material structure here. And the Y polarization doesn't show the any response. That means the Y polarized the acoustic mode are generated using this structure, and the wavelength is located here. Okay. Okay, we use the femtosecond laser. The pump power is the pump wavelength is 1560 nanometer, and we first measure the third generation, and the other thing is the nonlinear absorption coefficient. Okay, so first we measure the third generation by using this pump laser. Okay, so the red line shows the third generation from the MXene plasmon structure, and the blue line shows the quartz and MXene, but not acoustic mode, just the MXene plasmon model. And the black line shows the quartz. Okay, so this is the absolute value. Quartz is very large, very thick structure. Okay, so if we compare these two values, we can see that the M model shows the 300 times larger than that of the quartz structure. And the N model also be higher, it has the 168 times larger the third order generation compared to that of the pure MXene structure. Okay, so third order generation is highly enhanced in the MXene acoustic MXene structure. Okay, we further measure the nonlinear absorption coefficient, nonlinear absorption property of this the MXene structure. Okay, so the nonlinear absorption can be expected to this from this to the MXene structure. Okay, so this is the this is the nonlinear absorption spectrum. So using this same intensity, okay, we can clearly compare them. Only the MXene, so only MXene shows like this here. But the M resonator shows the very extremely large absorption in the this input powers. Okay, so we can compare the nonlinear absorption coefficient. We can extract the absolute nonlinear absorption coefficient from this absorption spectrum. So we can clearly compare the exact values of the absorption coefficient, the nonlinear absorption coefficient with the different 2D materials. So clearly we see that this is the no acoustic mode, just the pristine MXene plasmon structure here. And we can clearly see that other 2D materials shows compared to the other 2D materials, the MXene structure shows the large nonlinear absorption coefficient. But if we use the acoustic mode structure using this the MXene structure, we can further increase the 2 orders of magnitude enhancement using this acoustic mode structure. Okay, so we clearly find that this is the dispersion. Okay, so this K vector, and this is the wavelength, and this is the terahertz, long wave infrared, mid IR, and the short wave infrared. Okay, so other materials like the other 2D materials shows that the plasma frequency is located in the low wavelength region, okay, low frequency regions. Sometimes the TMDC material shows the increase of the frequency to the stabilized region, but the wavelength is still very low. This is a very exceptional material, so to the TMDC material. Okay, and this is the noble metal structure, and the MXene structure is located in this region. So a large frequency and large K vector regions. So MXene can generate the large wave vector plasmon mode in the SWR region. Okay. We can also use this MXene structure as the fingerprinting device. Okay, so for example, graphene also show the graphene or other metal structure can detect the molecular vibrations directly using the large field confinement. So molecular vibration and the field confinement is highly overlapped. So we directly measure the molecular vibration frequencies using this transmission or reflection spectrum. 2D material can also be measured, right? If you see the graphene plasmons can measure the mid-IR, very long wavelength regions, the IR spectrum, the molecular vibration spectrum can be observed using this, the plasmonic field confinement property. Okay? MXene can cover, okay? MXene also can cover graphene plasmonic vibration mode. Graphene plasmonic frequency can cover the MXene, and even the MXene plasmons can cover the metallic plasmonic mode. Okay, so graphene, the MXene plasmons can detect all the signals in the IR region of the molecular vibrations. So we fabricated this ladder structure, the gold ladder structure, and we located MXene, and we put the PMMA polymer between the metal and the MXene layer. So we want to see the vibration mode of the PMMA polymer layers. The PMMA polymer layers has the several vibration frequencies like that. So if we use the MXene gap plasma, okay, MXene structure, okay, gap plasma, MXene plasma, so we can more clearly see the molecular vibrations of these the PMMA or any other materials within a very large broad ranges. Okay, so this is a measured structure, a measured reflectance spectra, so we can clearly see the molecular vibration frequencies, even the short wave, even the long wavelength regions and the very large long wavelength regions and short IR wavelength regions. We can measure the entire spectrums of the molecular vibrations using the MXene plasma structures. Okay, so today, so I show the MXene plasmas. Okay, so MXene model can be generated. MXene plasma model can be generated in the SW region. Okay. Okay, so adopting the acoustic plasma model, we can further increase the field confinement, okay, in these plasma structures. With a strong coupling with the light to MXene through plasmas, it shows the very giant nonlinear responses. We can also detect the molecular fingerprint in the broadband infrared regions. Okay, so this is our group members, and I appreciate Professor Jong-Min and Professor Yuri Goch. Okay, thank you for your attention.
Thanks for the nice talk. We have time for questions.
So great talk. I have a couple of questions more for my conceptual understanding, which is when you measure your MXenes, they are clearly not monolayers. They are few layers stacked.
Yeah.
Right? And there is a highly conducting, high carrier density region, which is the central metal atoms, right? And then there are the surfaces which are largely non-conducting. I believe. Is that correct? The functional surface functional groups, plus the van der Waals gap, I would think they are not conducting. So when you model these structures electromagnetically, will you need a effective medium model, or do you just
yeah, that's a very good point. Yeah. So we still are working for the theoretical analysis of this the MXene structure. It's quite difficult for us. So in this measurement, in this study, we just use the final values of the permittivity. Okay, so this permittivity include all the properties of your.
This is electrometry measure. Right?
Yeah, electrometry measures.
And you're basically using it as a continuous medium.
Oh no, just we changed the thickness of the.
No, but within the thickness, you are modeling it as a continuous medium. Right?
Yeah, sure.
So 5 nanometers is fully continuous.
Sure.
That's how you're modeling.
Yeah.
But your TEM shows that cannot be assumed to be true.
Yeah, effective value, right.
Which are clearly insulating in between this.
Yeah, good point. Yeah. So electrical conductivity is the in-plane directions. The out-of-plane direction, electric conductivity is very low. Thermal conductivity also very low. Okay, so electric conductivity is generated along this direction.
This further suggests that you may have to use some kind of effective medium where the intermediate spacings, right, are largely insulating.
Sure. Yeah.
Right? You may have to model them as vacuum or some other type of medium.
Yeah. Good.
And then the actual MXene layers, their permittivity may come out to be different if you use an effective medium model.
Yes. Right. Yeah. Very good point. Thank you for the question. A good comment. So the other interesting property of MXene is that the large conductivity has a large conductivity and the small thermal conductivity along this direction. This shows it has the simultaneous insulator and conduction properties. So we can use that structure as the other the applications.
The second question I have, which is related to this, is the carrier density that you determine about 10 to the power 15% square, right? It's a very impressive number.
Yeah.
But I'm wondering, is this back calculated or back extracted from optical measurement, or is it something that you truly measure directly via some kind of hallmark measurement or hall measurement?
Sorry, I didn't give the reference the journals, but we get the values from the other journals. This value, yeah, PI350 MXene.
But do you know what type of measurement they use?
Sorry, I have no idea about that. Yeah, good, thank you. Yeah, so okay, yeah, so MXene has the large conductivity, conductivity. That means the carrier density and electron mobility, right? The combination of these two values. So MXene has the large electron density, but very low mobility. Okay. Graphene has the very low electron density and large mobility. So MXene's conductivity is very similar to the graphene, but the origins are very, very different. So graphene cannot go to the largest plasma frequency. That means there's low electron density. Okay, thank you for the point.
Okay, we have time for one more quick question if there is one.
And my question is related to PMMA. You mentioned like PMMA once, and what I just know about this PMMA is like I heard it can be used to fabricate, like for example, like micro cavity lattice. But in your case, why are you using PMMA?
Most important part is that it's very easy to make the PMMA structure because we didn't get a chance to get the various types of the polymer. So just we try to measure the PMMA, but in that structure we clearly analyze the responses.
Okay.
Yeah, there is no other reason. Easy to get this structure.
Okay, so we're out of time. If you go to the next talk, let's take the speaker.
Thank you.